Welcome. So this is 2048, it's section A, and this is video 2. And we're going to look at some mathematical sections now. We're going to begin by looking at math that you absolutely need to know. Secondly, we'll look at units. We need to know units, but we'll be learning units and prefixes. And we'll find that prefixes have some complexity to them. The prefix pattern we use for mass is not the same as the prefix pattern we use for distance and time, and the prefix pattern we use for area and volume are not the same as we use for length. So there's a little bit of complexity, and then we'll do some examples to practice these things. Okay. So this is math. I'm sure you've done most of this before, but I need you to know it pretty well. So the first thing is computational skills. I know it sounds obvious, you need to be able to compute, but people make calculator errors all the time. A classic one is if you said 21 divided by 3 pi. And people will put into their calculator 21, and then they'll press divide, and then they'll press 3 and pi. And they'll get an answer which is probably going to be round about 22 or 23. And the reason is because the calculator thinks they want to take 21 and divide it by 3, and then you want to multiply that by pi. So you get 7 times pi, which is more than 21. The way you get round this is you'd say 21 divided by, then use parentheses, and you say 3 pi, enter. Or you could say 21 divided by 3, enter, divided by pi, enter. That will get you the right answer. The right answer should be, well, it's going to be about 3.5. So two messages there. One is make sure you're using the calculator right and pay attention when you get the wrong answer. It's not always just a slip, sometimes it's technique. And the second thing is always look at your answer and say, does it make sense? Use a little bit of mental judgment and say, does this calculator answer make sense? We don't like dealing with very big numbers and very small numbers, so often we use prefixes. There are a million prefixes, but we deal with these. We deal with pico, nano, micro, milli, centi, kilo, mega, giga, and tera. And those are the ones I want you to know. I expect you to know those. Deci, deca, we don't use very much, and there's others we don't use at all. But these are the ones that are fair game, so make sure you're comfortable with those. You know the symbol, you know the name, you know the numerical value. We'll talk about scientific notation. 2,400 meters could be written as 2.4 times 10 to the 3 meters, or 2.4 e plus 3 meters. That's the engineering notation. I wouldn't particularly use scientific notation on that number there because there's not enough zeros. But if I was dealing with, say, 5260000, I would definitely use scientific notation. And if I was dealing with 0.00000025 meters, I'd definitely use scientific notation on that. At the next level, you'll be expected to be using scientific notation just all the time when it's needed, so get used to it. Algebra, you've got to be able to rearrange equations and find the roots of quadratic equations. It's just something we do, so that shouldn't be the problem. The problem should be the physics. This is a technique we just need to be good at, so go back and review that if you need to. Recognizing linear equations, extracting its y-axis intercept, getting the slope and the area under the graph, and being able to plot the graph. All that stuff that you did many years ago, you got to go back and review. Geometry. For most engineers and physicists, switching between a sphere and a cylinder and a cube is no big deal. It's like changing the color on an illustration. It's no big deal. But if you don't know those equations, it's devastating because you can't do the problem. So I need you to know these parts of geometry. I'm very specific. I want you to know these parts of geometry. I want you to know the equations for the circumference of a circle, the area of a circle, surface area of a sphere, volume of a sphere, surface area of a right cylinder, volume of a right cylinder, area of a triangle, area of a trapezoid, number of degrees in a circle, number of degrees in a triangle, number of degrees in a straight line. These questions, I will ask you about these in some exams. I'll just say, well, what's the equation for the surface area of a sphere? And if you know it, it's easy points, and if you don't know it, you've lost some points. So make sure you know these. And then trigonometry. I don't need a lot of trigonometry, but what I need very smoothly. So for example, I need you to know about the sine, the tangent, and the cosine, and the inverses, of course. But here's the thing. So people get used to doing, so there's a vector, we'll say it's f, and there's an angle, that's theta, and I say, well, what's the x component of that vector? So I visualize a little vector to the side, and trigonometry tells me that this value is f cosine theta, and people go, well, yeah, that's clear. But here's the realistic situation that we face. There's a slope and there's a weight. And now I want to find the component of the weight along the slope. So I have to draw a different triangle, which gives me a different vector. Here's the angle theta, and I say, well, that is w cosine theta. And that gets people's attention, because that's not so obvious to them, because the geometry is slightly different. I need you to be able to do things like this. So if you're not comfortable with doing sines, cosines, and tangents at this kind of level, then please go back and review. And then in terms of calculus, I need you to be able to differentiate and integrate relatively straightforward functions. This is not a calculus class. I'm not going to throw some weird function at you without warning and then say, well, integrate this. So basically make sure you're solid on differentiation and integration for simple, quadratics and things like that. Units. When somebody says to me, but I got the right answer, but the units were wrong, I cry on the inside, because it's like saying I paid you 5 cents rather than $5, but it's okay because the number's right. There's a huge difference. So we need to pay attention to units. Different organizations have different unit systems. Some use the imperial system, for example, the United States in certain parts. Some people use the MKS system, that's the meter kilogram second system. Some people use the CGS system, that's the centimeter gram system, and we use the SI system. Most developed countries in the world use the SI system. It's basically a slight modification on the MKS system. Our equations work when we put in numerical values that have the right units. So if the equation is designed for the SI unit, so length should be in meters, and we put the answer in inches, it's not going to work. So we've got to get familiar with changing things to the SI unit. So lengths must be in meters, masses must be in kilograms, and time must be in second. We can have combined units. So speed, which is a distance divided by a time, will be in meters per second. Area, which is 2 independent lengths, will be in meters squared. And force, well, now force, I know from physics that F equals ma. So force is equal to kilograms, meters per second squared. And a bit sadly, they decided to name that unit, the kilogram meter per second squared, after a famous scientist. So they named it the Newton. The sad bit is that as a student, if I saw that the answer was in kilogram meters per second squared, I knew that I would have to find a number that was in kilograms and multiply it by a number that was in meters per second squared. So in a way, it told me how to do many of the problems. By naming the unit after Newton, we've lost that trend. So you're just going to have to learn what a Newton is. We do use prefixes quite a bit. We don't like to use, in speech, we don't like to use powers of 10 very much. So we tend to use prefixes. Rather than saying that I have 5 times 10 to the 12 newtons, I say I have 5 teranewtons. And we understand what that means. So I need you to be very comfortable with these terms: tera, giga, mega, kilo, centi, milli, micro, nano, and pico. And I need you to know the symbols, so uppercase T, uppercase G, uppercase M, lowercase k, lowercase c, lowercase m. A Greek symbol, mu, lowercase n, lowercase p. Notice, uppercase M, lowercase m. You need to make sure your writing is not confusing. And then what do they stand for? 10 to the 12, 10 to the 9, 10 to the 6, 10 to the 3, 10 to the minus 2, 10 to the minus 3, 10 to the minus 6, 10 to the minus 9, 10 to the minus 12. And we apply these. So for instance, if I say I have 1 megameter, I know that that is 1 times 10 to the 6 meters. Or if I have 1 micrometer, I know that's 1 times 10 to the minus 6 meters. That makes sense. And time is the same thing. If I have 1 megasecond, it's 1 times 10 to the 6 seconds. And if I have 1 microsecond, it's 1 times 10 to the minus 6 seconds. Here comes the catch. We don't base our mass unit on the gram, we base it on the kilogram. So if I have 1 megagram, it's not 1 times 10 to the 6 kilograms, it is 1 times 10 to the 6 grams. And so if I need to be an SI unit, I have to convert from grams to kilograms. And I know that there are 1,000 grams in a kilogram. So my 1 times 10 to the 6 grams becomes 1 times 10 to the 3 kilograms. In effect, I added minus 3 onto the power. By the same token, if I have 1 microgram, I have 1 times 10 to the minus 6 grams. But because I got to work in kilograms, I have 1 times 10 to the minus 9 kilograms. Again, I added minus 3 onto the power. So please make sure you get comfortable with these things and you don't make mistakes on them. And the second part of this is doing length, area, and volume. If I have a meter, there might be 100, well, there are 100 centimeters in the meter. If I have a meter square, then I have a whole bunch of little squares, and there are 100 columns of 1 centimeter squares and 100 rows of 1 centimeter squares. And when you multiply that out, there's going to be 100 times 100 little squares. And if I go to a volume, so now I have my volume, I have 100 of these little plates, little shields of squares. So I have 100 times 100 times 100 little cubes. It's logical when you perceive it right, but it can be confusing at the start. So the first thing to do is to set an alarm so that you know there's an issue. And then the second thing to do is to learn how to do it properly. So again, so let me emphasize this. When I say 1 megameter and 1 megagram, meter squared and 1 megameter cubed. It's not 1 megameter, 1 megameter squared and 1 megameter cubed. It's actually, well, it's 1 megameter, 1 megameter squared and 1 megameter cubed. Can you see the difference between those? I'm not applying the prefix to meters cubed. I'm applying the prefix to the length and then I'm cubing it. So I get different numerical values. So 1 megameter is 1 times 10 to the 6 meters. 1 megameter squared is not 1 times 10 to the 6. It's 1 times 10 to the 12 because I have 10 to the 6 in one direction and 10 to the 6 in the other direction. And 1 megameter cubed is not 10 to the 6 meters cubed. It's 1 times 10 to the 6, 1 times 10 to the 6, it's 1 times 10 to the 18 meters cubed. And by the same token, 1 micrometer is 1 times 10 to the minus 6 meters. 1 micrometer cubed is 1 times 10 to the minus 12 meters squared. And 1 micrometer cubed is 1 times 10 to the minus 18 meters cubed. So it's not impossible, it's quite logical, but if you're not thinking about it, it's easy to make a mistake on it. Best thing to do is practice. So here's a typical question. It says convert 24.5 picometers into standard SI units. The first thing I would say is don't change the 24.5. There's no rule in SI units saying that you have to have 2.45. So just leave the 24.5 alone. So I have 24.5. And then pico. Well, pico's 10 to the minus 12. You've got to memorize that. So that's going to be times 10 to the minus 12. And the units is going to be meters. And when I check your answer, I check all of it, and it's all got to be correct. So if you make a mistake on the units, you've lost the points. If you make a mistake on the prefix, you've lost the point. This is something where you know it's going to come up, so I want it to be exactly right. So the correct answer to this would be A. On this next one, it's 27 milligrams. So got to convert that into SI units. So that's going to be 27 times 10 to the minus 3 grams. That's correct, but it's not SI units. I have to convert to 27 times 10 to the minus 6 kilograms. Notice I added minus 3 onto the power. And again, when I'm grading this, I'll look to see, do you have the right units? Do you have the right numerical value? Did you leave the number alone? If you changed it to 2.7, you got to do the correct numerical change for the power. So you're adding a complexity to it that you need not do. But the correct answer to this then is 27 times 10 to the minus 6 kilograms. So the correct answer to that would be D. And then the third one is 17.2 micrometers squared. So that's going to be 17.2. Micro would be 10 to the minus 6, but there's 2 dimensions for it. So it's 10 to the minus 6 times 10 to the minus 6, which gives you 10 to the minus 12. That's 10 to the minus 12. And then I've got to remember I'm dealing with an area, so it's got to be meters squared. And again, I look to see, do you have the right units? Do you have the right power? Did you mess around with a numerical value? And it's all got to be correct on this example. Notice here, 17.2 times 10 to the minus 12 meters. That's not the right answer. 17.2 times 10 to the minus 12 meters squared. There's the right answer. So we expect the numerical value to be correct, and we expect the units to be correct. There we have it. Thank you.